Hello, everybody, and we are going to start our second lecture in signal and system. Last time we discussed Fourier series part 1, and today we are going to look into Fourier series part 2. As you can see from my slides, I just prepared the slides for Fourier series part 2. You can see that um, right at the starting, I'm talking about what is a Fourier series. So let me see what I mean when we look into periodic signals and we wanted to analyze them using Fourier series. So what we mean is that the basic principle behind Fourier series is that if you take some sinusoids, when I say sinusoid, I mean sine and cosines. And if I add them, and you know how the waveform are added, they are added sample by sample. So for example, if I want to add this part, then I have to pick. So if I add this part, then I have to pick a corresponding part here. So this part will be added with this part, and that's how I will end up into getting this particular value. Now this is a positive value and this is a negative value. So this positive value is subtracted from the negative value, and that's how you get this small negative part. So let us say I pick this part. Now here is a negative part, okay? And if I look at the exactly same part on the next wave, it is small negative. So overall, this is a negative part, this is small negative part, and when we see and we add them, what you can see very clearly is that if I just look at, it's a very big negative part. So this particular wave that I'm watching right now, this is a resultant wave that is constructed by adding those time samples. But we have to take the same time instant. So think about it, this is a time axis, this is another time axis, but we have to pick the same time instant. So if I pick a time instant, this one, then I have to pick the same time instant here, okay? And then when they add up, their answer has to also plot it against the same time instant on the resultant wave. So you can think of it that this is waveform 1, which is also a sine and cosine, and the waveform 2. And when I add these 1 plus 2, I'm getting this wave equal to 3. So this one is a resultant waveform. And you can see very clearly that the resulting waveform has a shape that does not resemble that much with its constituent waveform, which are sine and cosine. So it means that if you add sine and cosine with different periods, then there is a chance that we can reconstruct in our signal processing language, we call it synthesize very complicated waveforms. And some of the waveforms were so weird that probably most of the scientists at that time does not agree with Fourier that these waveforms can be constructed from sine and cosine, because sine and cosine are fairly smooth waveforms. It doesn't have those edges, but you can make complicated waveform with edges from these smooth signals. However, this was true. Similarly, I want to give you another example here. So let's say I wanted to make a square wave. So if I take this wave, which is a sine x, as you can see very clearly, and if I add this to another sine wave, but this time this is sine 3x, you can see very clearly, this is sine 3x, this is sine x. Now what's the difference between sine x and sine 3x? Let's look into that difference. So difference between sine x and sine 3 times x. Now it is the same waveform, sine and sine. It's not like this is sine and this is cosine. But the difference comes up in the argument. The argument of this one, the argument here is x. The argument of this sine is 3x. So the difference is in the period. So for example, the time period of this sine is, we always put 2 pi by omega. Now what is omega? Omega is a constant that should appear right next to x. So in this case, the omega is 1, so it means the time period here is 1. Whereas the time period for this one, where is sine 3x, this is t equal to 2 pi by 3. So you can see very clearly there is a difference in the time period. The time period of this one is, I just make a mistake, it's not 1 actually. The time period of this one is 2 pi, okay? So, and the time period of sine 3x is 2 pi by 3. So I can just put here, this time period is 2 pi by 3, whereas the time period of sine x is 2 pi. It means the sine x will complete its one period in 2 pi, and that's very obvious. It is doing it. You see, from this. So if I say one time period that I can write down from here till here, this is the sine x, and then the period is from minus pi to pi. So obviously this is 2 pi. Whereas now if I look at sine 3x, and if I just look at its one period, okay, so its one period is starting from here and reaching till here. So you can see that this is the time period. If I start from 0 and I look at it again, so it will be going till this point. So now you can see very clearly. This one is 2 pi by 3. And look at this, how much? This was complete 2 pi, but this now shrink to only 2 pi by 3. This is a very small area. So if I just look at the area, this area from here till here, this is 2 pi. This is the length. And the length of this period from here till here, this is 2 pi by 3. So it means that this is a higher frequency component because its time period is small, as we all know that there is an inverse relationship between the frequency and the time period. So as the frequency increases, the time period decreases, shrinks. So you can see that. So this is a high frequency component. I can say this here. This one is a higher frequency component. And this one is a lower frequency component. But what we are stressing right now, and what Fourier was stressing, was that if you give me sine and cosine and you allow me to change their periods, it means I can have sine x, I can have 3x, sine 3x, sine 5x, sine 8x. So it means if you allow me to change their time periods, and then I can add them, then I can make anything that is really far away from their individual component shape. So as you can see very clearly here that if we add these two, so if I'm going to add these two, okay, and here I am, I'm going to add this one with the previous one, okay, and what I'm going to get is equal to this one. Now this resembles a square wave. And you will probably see that the square wave have much sharper edges. It goes from 0 to 1 in a very short time interval. Whereas the sines from which it is made up, these are smooth. They don't have edges. They don't have rough edges, and they take time. For example, going from this one to this -1 values, okay, this one, it takes some time. It is traveling, it takes some time. So it means there is a time that need to be spent. So for example, this is a time. It needs to take this much time in order to go from top to the bottom. Whereas in case of a square wave, that is kind of abrupt. It goes from 0 to 1 in a very short time, delta t time. So it means that we are able to make waveform which have very short and transition time, which are very much abruptly changing from lower value to higher values. We can make them from couple of sine and cosine waveform, which we don't have that sharp transition. They are smooth. And in many cases, it happens that these waveform doesn't have, because they are with sharp edges, they don't have what you call them differentiability at these points. Whereas the one waveform from which they are made, they do have that differentiability. So the sine and cosine are differentiable, whereas these waveforms are not. But still, it's really amazing that you can make those complicated, short transition, sharp edges from waveform which don't have edges and which are smooth. The only thing we are playing the trick is we are changing their periods. So if you give enough addition of sine and cosine in which you play with the periods, you can make the waveform that you're looking for. So this is called synthesis. Okay. So let's move towards the next slide. Okay. Which is, and that's really amazing. And that's what I was trying to put forward. The message last time was that there was a person who is calling a doctor and saying, hey, Dr. Elizabeth, yeah, oh, I accidentally took the Fourier transform of my cat. So now look at this. The moment he took the Fourier transform of the cat, and if the cat was being transformed, it will look something like this. Okay, because this is the Fourier transform of the cat. It will have some peaks, then come back, then have some smaller peaks, then another peak, then after some. So this axis, the one that this waveform is going, this is omega axis. So this is a frequency axis. This is not a time axis. Whereas if I look back at this particular cat, and the axis I'm looking at, the axis here is t. So in t axis, I see cat. But when the same cat, I look at in frequency domain with respect to omega, I see those peaks coming up here. Okay, and every peak is just telling me some characteristic of the cat, but it does not mean that the cat has been changed. It will look like the cat that we are watching right now. So this is the real life cat. So this is our real life cat. Okay, here is this also represent a cat, but this is the Fourier spectrum, or I can say spectrum of the cat. So let me write it down. This is spectrum of cat. So we took the spectrum of the cat because now we are watching everything with respect to omega. There is no time here. Everything is with respect to omega. Now each of the peak is telling me something. For example, this peak may be telling me that the cat is alive. Okay. And yes, sure, cat is alive because in time domain, it's a live cat. Now this peak, particularly the second peak that I'm watching, this is telling me that this peak is mad at you. Okay. So in other words, these peaks in our Fourier domain tells us some characteristics of the cat that we may not know when we look at the real life cat. So for analysis purposes, we take the Fourier transform, but Fourier transform is for analysis. So keep in mind, Fourier domain representation. So my stress is, please, to call, whenever you look at Fourier domain, you can say representation. Don't say conversion. representation. So Fourier domain representation actually tells you some features of the cat that may not be that obvious, that may not be that obvious from its time domain representation. So we change the representation and we look at from a different perspective just to see some features that may not be obvious. Last time I give you example of someone whose hand was, the bone of the hand was broken, so he has to take the X-ray. So X-ray tells us where the bone is broken so that we can put the plaster around it, but it does not mean that when you take the X-ray and when you take the hand out of the X-ray machine, your hand has been transformed. It is no longer the same hand. No, it remains the hand. The only thing was you were not able to see and analyze what happened to your hand unless you took the X-ray. So it means that it's a kind of watching something for the analysis purposes. But when you're watching, you're trying to make some kind of decisions about the processing. But this whole process, when you're watching something and you still have to make some decisions regarding its processing, this is called analysis part. Once you start processing, that basically means that you employ filters now, and those filters will be able to remove one or two particular frequencies that are undesirable. You don't like those frequencies because those frequencies are associated with the noise present in the signals, and you want to clean up the signal. So this is like a very common example of filtering operation. So that may be something that you would like to do. However, the Fourier domain representation helps you in analyzing the signal in a much better way than we can in the time domain. So it's like a analysis tool. So it's like a tool that let you see certain features that may be not that clearly visible in their time domain representation. And when we see frequency domain representation, then we have two things in our mind right now, which is one is Fourier series, another is Fourier transform. But since I'm dealing right now with periodic signals, so I will say whenever I'm talking about Fourier domain, I invariably am thinking in back of my mind about Fourier series. Okay, good. So now let's move towards another picture that might also explain to you. You see there is an equal sign right here. So in other words, you can see this is an equal sign. Let me put another color because that color makes more sense. So here is an equal sign that we are watching. And this equal sign came from summing these three waveforms. The people are having those. This is a very low period. It has a very low, very large period, but low frequency signal. This is a rather higher frequency signal because the time period is smaller here. This one is much higher frequencies. But look at them, the amplitude is decreasing. The amplitude of this waveform is from here till here. So the jump is really big. And the jump by the waveform having this lady in the hand is smaller. And whereas the jump here, so it means as we go to higher and higher frequencies, our Fourier analysis tells us that the amplitude of that component is also decreasing. So when we say infinite sum, what actually we mean in real life that after, let's say 18 or 19 terms that we add, we stop because now the effect of any other term that you add in the overall waveform of the picture is not going to affect too much. So we will stop here. So this is how you can see very clearly here that these waveforms, when these three are added, we kind of getting this square wave. So this is an approximation of the square. But this is kind of our belief, okay, approximation of which wave? The wave that I'm talking about, like this, okay? So this is the wave I'm talking about. This is an approximation of that wave. But you should keep in mind that this approximation will get better and better. It means all these ripples that you see and Gibbs phenomena at the edges that you will see, these all will subside as you move more and more components. Although the Gibbs phenomena is like really subtle phenomena, it never goes out completely. But anyway, we can reduce the impact of the Gibbs phenomena at the edges. But these are the overshoot that happens at the edges. So these approximation will get better and better in terms of the shape will go better and better as more and more components are added. So the Fourier series components are mostly sine and cosine. Okay, and when you add them, then you get this waveform. Okay. The other slide that is worth looking at is this one. One can argue that if I already have a waveform, so let's say we have a waveform which goes like this, then comes down, then goes up. So if you have this type this particular waveform in front of you, this waveform, why would you break it up and decompose it into those sine and cosine? Why you want to represent it in sine and cosine? The reason is that the sine and cosine are infinitely differentiable. And these are like kind of a desirable waveform in mathematics. When something is differentiable, it means that it is differentiable at each point, okay? Then this particular waveform is desirable because we can do lots of other mathematical nice operations on it. However, if there is a waveform where there are edges, the one I'm just showing you right now this edge does not have that property of differentiability. It is a discontinuous part. So in this case, then most of my analysis and most of my mathematical tractability or application will be kind of limited. I have to make some certain assumptions about the continuity of the signal and mean square sense. But it will not be an equal operation. This particular part will be really difficult to process. That's why we basically represent this complicated signal by these infinitely smooth waveform that I'm just speaking right now. And because these particular waveform, these terms can each be separately processed quite easily as compared to the original waveform. Okay. So that is one particular argument in favor of why we have Fourier series. Okay. So let's go to an example here. And this example is about a square wave. We are given a square wave. Okay. And we are asked to find now why I call it square wave. The square wave means that it has almost a 50% duty cycle. 50% duty cycle. Now what is duty cycle? Duty cycle means that in one particular period, how much time it was on versus how much time it was off. So you can see very clearly here that from minus pi to plus pi, okay, so if we just do this, from this time till this time, it is off. Then it is on for this particular time. From here till here, this is on. And then it is off from here till here. So this particular time that I'm looking at right now, so this is off period, then on period off. So if we add these two off period, then this becomes equal to on period. That's why I'm writing 50% duty cycle. Okay. So this waveform is called square waveform. So it is on for half of the period and off for half of the period. So on half the period, and then this is off half of the period. Okay. Now our point is that this waveform that we are watching right now, we are watching it in time. Look at this axis. It's very important to look at what is happening here. This is not omega, this is t. So it means that this waveform is in time domain. So this is a time domain picture. Time domain picture. So this is a time domain picture because of this particular thing. Sorry, I can put an arrow here and show you. So once you see this T with an arrow on this axis, that means that this whole picture is the picture that you will see probably on an oscilloscope. So if you have an oscilloscope, you will have the screen, then you will have those buttons, volume, sweep time, and there will be these other displays, channel 1, channel 2, and here you will see this waveform. So this one, the whole thing that this whole is your oscilloscope that you see in electronics most of the time. So this waveform is exactly this one. This waveform is that you are watching right now. So if you want to see a time domain picture, you have to go and give that particular signal to channel 1 and channel 2, and then turning the sweep time, you can see that particular waveform on the screen. So this is our square wave, okay? And now what we want to do is, we wanted to find its Fourier series. So when we say that we wanted to find the Fourier series and plot the spectrum, you can see that here I'm talking about spectrum. So when we say that we want to sketch its Fourier spectrum, then I know that it's not Fourier transform that I'm going to sketch. I'm going to sketch Fourier series. The reason is because it's a periodic waveform and it's periodic in time. I can see very clearly. So looking from this perspective, I can say that our question is rather this one. Can we take a periodic function and represent it as an infinite sum? Okay, infinite sum means that when I take sum, the terms are not finite. Terms are going from n equal to 1 to infinity. So many terms. Infinite sum means this particular notation. So infinite sum of cosine plus infinite sum of sine. So this is the whole idea. Can I represent my signal x of t equal to something like this? So can I put my xt equal to infinite sum of cosine plus infinite sum of sine? So can I do this? However, the whole idea is that these sine and cosine will have different periods. Okay, so in order to cater this, I have to put in the argument that I'm talking about right now. So this argument is n omega naught t, n omega naught t. So this argument that I'm talking about, this one, okay, and this one, basically I'm catering to this particular word, different periods. So when I'm saying different periods, it means that I'm going to give different value to n. So n omega naught represents, okay, this n omega naught represents different periods. Okay, so this n omega naught is a different period. So I have to put them this. So infinite sum of sine and cosine with different periods. So that's how I complete my Fourier series representation. But in reality, there is an a naught also in the beginning. So I can say a naught here and then plus. So a naught represents DC bias, whether the waveform was lifted from the ground or whether it was on the baseline. So I will tell you more about it, but anyhow, so right now you can think of it that can we represent this periodic signal as infinite sum of sine and cosine with different periods. So the Fourier came and he basically has an answer, and his answer was resounding yes, yes, we can do it. Yes, sir, we can do it. He was in French army, so he probably have said the same thing. Saluted and then said, yes, sir. But the question was how, and when the question was how, then we have to basically go and find the values of a naught, a n, and b n, which basically makes the so you can think of it here is an a n, here is a b n. Okay, so these are the weights that we need to find. How much is each frequency is contributing towards the overall shape of the signal. Okay. So now let's move towards finding those A naught. So our aim is to find A naught, A n, and just clean up this thing. So A naught, A n, and B n. So this is our aim. We are going to find these weights, because the weights will tell us the contribution of each. So if, for example, some weight is 0, that means that particular frequency is not present in that signal construction. And that signal does not contain that frequency. Now it's a periodic signal. So when we declare that a signal is periodic, then what we mean is that it has a non-zero period. So you cannot declare 0 as a period. Otherwise, then DC signals, which does not repeat at all, does have 0 period. But when we talk about periodic signal, we specifically think about the signal which have a non-zero period. So it means period has some finite values in terms of time. So there is a time interval. So I can say a period is a finite time duration. So there is a finite time duration, and after that finite time duration, the signal repeats again over and over again. So that's how it is called periodic signal. You can see very clearly from here also that this is one period, then it repeats, and here is another period, and similarly on this side also it is repeating from some previous time till the final time. So it's repeating all the time. After that particular time duration repeats. So what is the time duration that it is repeating? So the time duration is the smallest possible time interval after which it repeats. And if you look into this, the smallest time interval is minus pi to plus pi. So the period of this particular square wave is 2 pi. So it's a periodic, and it has that period 2 pi. But keep in mind, this 2 pi is the time. So it is the units are seconds. Don't think it is 2 pi is an angle, okay, or 2 pi radians. No, this is 2 pi seconds, because we're talking about time. And the frequency, omega naught, the fundamental frequency, and it's the formula for the fundamental frequency is 2 pi by T naught. So 2 pi by T naught. So one is radians per second. Okay, so radian per second. So this is the frequency. Okay, and here is this one represents this omega naught. So now we got it. So T naught is 2 pi seconds, and omega naught is 1 radian per second. So once we have T naught omega naught, now we are in a position to write our Fourier series. So our Fourier series now become A naught, okay, then infinite sum, okay, then A n cosine n omega naught. Now keep in mind this term is omega naught, and omega naught is 1. So this becomes cos nt plus summation n equal to 1 to infinity Vn, which is the weight of the sine nt. So in other words, I can write it very fairly easily now that this is a naught, but there is then this infinite sum, n goes from 1 to infinity, a sub n, which are the weights cos nt, plus summation n goes from 1 to infinity, b sub n, and then sine nt. So here is my Fourier series for my square wave. This is my Fourier series for my square wave. However, I don't know those weights. The only thing that now I'm worried about is I don't know about those weights. So if I just take my weights, I don't know this, I don't know an, I don't know bn. So my aim is to find a naught, an, bn, weights associated with sine and cosine components. So these weights will tell me whether this component is eligible for the addition or not. If the weight is small, I will not like to add it. And if it is, then I will think of it as a contributing factor towards my final x of t, which is square wave right now. Okay. So if I move to the next one, we have to find now a naught. Okay. So first we find a naught. A naught is 1 over t naught integral over 1 period x of t dt. Now this particular formula can be easily evaluated because now we know that the time period is 2 pi. Okay, this is our 2 pi. And we pick the period because we can pick any period. So for our convenience, we know that it is much better to pick from minus pi to plus pi. Okay, so we go from minus pi to plus pi to take advantage of the symmetry of this because it is on both sides of plus and minus. So minus pi to plus pi x of t dt. And now if you go from minus pi to plus pi, you will find out that it's not a continuous waveform that you see from minus pi to plus pi. What we see is then there is a kind of off period, then suddenly it turned on and then off. So in order to cater this, we know the properties of the integration is, because integration is an area, I can divide the area into smaller areas and add them. So I will take first from minus pi to minus pi by 2 because that's where the signal behavior is changing. Okay. And then I will take another interval from minus pi by 2 to plus pi by 2. Okay. And then finally I will take pi by 2 to pi. So I will take my integral, if I can write it here, my integral from minus pi to plus pi. I break it up into 3 integrals based on the behavior of the signal that I'm going to integrate. Minus pi, okay, minus pi to minus pi by 2. Then another integral I got, which was going from minus pi by 2 to plus pi by 2. And the third one I got from plus pi by 2 to pi. So I have to break this integral, the integral that I was watching right now. So this whole big integral, and I put it as this one plus this one plus this one. The reason is because of the behavior. The signal behavior is not uniform over all 3 integrals. And whenever the, sometimes we call it slope. So whenever the slope of the function is changing, then we have to break it into smaller intervals because integration is an area. So area can be added up to make the total area. So this is the total area, okay, which is equal to, let's say, area 1 plus area 2 plus area 3. So that's how we did it. Anyway, so if you do it, you will find out that the first one, excuse me, the first one is 0 because the height is 0. So that's how I get the overall integral is 0. Okay. And then I have 1. So if I integrate this 1 from minus pi by 2 to plus pi by 2, okay, look at this one. I will get some values. Then again, I got 0. So here is a 0, and here is a 0, because these two areas doesn't have any activity for a signal, so their integration is 0, because the area under the curve. But however, there is an area under the curve from minus pi by 2 plus pi by 2. You can see that here. This is an area that I'm right now putting the lines in. So this is the area under the curve. It has definitely an area. Okay. And that area I don't need to do even integration. I can just do, because it's a rectangle, you know, so the height of the rectangle is 1, and the base is from minus pi by 2 to plus pi by 2, so the base is pi. So pi multiplied by 1, so it should be equal to pi, and that's exactly what it is. So it's a pi right now, but I can do it geometrically, just looking at I don't need to do the integration at all. So pi, and there's the 1 over 2 pi already outside. So this term, when multiplied with a pi, you get a naught is 1/2, and we call it DC value. Okay. Now, what is the importance of a naught is equal to 1/2? That means that this whole signal is lifted from the baseline, and since lifted from the baseline, so it introduces this DC value. But however, if the signal was down, it means half up, half down, then this a naught will be 0, because then the upper area and lower area will cancel each other. So for example, if I go to next slide, I can show you what I mean by this. So for example, if your baseline was this red line, okay? So if this red line is your baseline, if your red line is this baseline, okay? Now if I take my Fourier transform a naught, then the area above and the area below will be 0. So in this case, if I use red line, my a naught will be 0. So a naught represents the baseline. So sometimes when we are doing this medical signal processing, we call it baseline wander. Baseline wander. That basically means that the baseline is fluctuating. Sometimes it is down, then goes up, then goes down. So this is your a naught, which is a DC value. So your DC value, which we call baseline wander, DC value is changing. And this happens in most of the sensors. When you take the values, the actual values will be somewhere lying on this baseline, and the baseline is going up and down. So the first thing that you do when you are cleaning up this signal is you have to remove this baseline, so that the whole signal comes down and is smooth like this. So in order to convert this into this one, you have to remove this red line, and this red line is your DC line, or we can call them baseline wanders. So this DC line has to be removed. So your a naught has to be removed. So in this case, if I remove the a naught, then the signal will go along the red line, which is my basis. Okay. So if you look into this, again, the same thing is this area from minus pi by 2 is 0, area is pi and 0. So if this is a vertical bias, in other words, if the baseline is down by 1/2, so imagine that if you lifted a signal and it goes up and your baseline is become 1/2, so then definitely there is no bias and a naught will be 0. So I have already explained this. Okay. Now let's look into trying to find this a naught, the weights for the cosine terms. So these are weights for cosine term. So the a naught is the weight for cosine term. But keep in mind, we are not considering n equal to 0, because a naught we already taken care of. We already taken this is a naught is already 1/2. We already know it. So it means that for n is 1, 2, 3, 4. So n is 1, 2, 3, and so on. But it's not 0 definitely. So if you do this operation, this is the formula that we're using. Okay. 1 over pi is just the coefficient that take it outside, and then you have this from minus pi by 2 to plus pi by 2 1, because this is the value of the signal x of t, because other parts are values is 0. So I have I'm forced to take the integration between minus pi by 2 to plus pi by 2 and cosine nt dt. Now look at this particular integration. So I'm forced to look at minus pi by 2 to plus pi by 2 cosine nt dt. Okay, great. Now for this one, I need to draw the cosine. Okay, so I need to know the period of this one. So let's say if I pick first of all n equal to 1, then I will get cosine t, and I'm integrating it between minus pi by 2 to plus pi by 2 dt. If I'm doing this basically means that I look at the cosine. My cosine, this cosine t has period 2 pi. And if I look at the signal, I can write right here. So between minus pi by 2, these two walls that I'm looking at right now, this wall and this wall, these are my two walls because this is pi by 2 and this is minus pi by 2. I can see that there is some area. Yeah, this is the area. Okay. Now, if I look at n equal to 2, now my signal become, now my integration become cosine 2t dt. The intervals are same. Cosine 2t has a shrunken period. So it means now between minus pi by 2 plus pi by 2, the whole period came in. So you look at the difference between here and here. These are the walls. These are the walls. This value is pi by 2 and this value is minus pi by 2. Now, if I look at this particular valve, then it's very obvious that this area is plus and these two are negative areas. Now, this positive and these two negative areas will cancel each other, and for n equal to 2, my integration will, this whole integration will end up into value 0. So that tells me that if I take the even values, sorry, n equal to 2, 4, I cannot take 0 because 0 is already found, 2, 4, 6, 8, and so on, then an is 0. However, if I take n odd values, that's what I said, then of course the area is not 0. This is not non-zero area between minus pi by 2 plus pi by 2, non-zero area. Now for this one, you can see very clearly that I have to integrate, and what I will integrate will become cosine nt will become sine nt, and this n will become in denominator, and I have this vector 1 over pi outside, and the limits are upper limit is pi by 2, lower limit is minus pi by 2. Okay. And now if I expand it further, but keep in mind this is for n equal to odd. Let's keep this always in mind because n is odd. For n even, we know that an is 0. So an is 0 for n even. So we are only talking right now, this is gone out of the scene. We are only talking about when n is odd. N is an integer, and we're looking at the odd integers. Okay. So if I do this expansion on our n pi, n doesn't have to do anything with the t, so I can take it outside, and inside I put the upper limit. Upper limit is pi by 2, lower limit is pi by 2, and this negative sign is inside the argument. And you know that sign is an odd function. So whenever you have an odd function, this negative sign will come outside, and when the negative sign comes outside, this will become positive. So these two are the same ones, so I can add them, and I can 2 times sine n pi by 2. You can see that this sine n pi by 2, and this is 2 by n pi sine n pi by 2. Now it's really interesting to see that the argument of the sign is that n times pi by 2. So the best way to look at it, I will write it like this. This will really make this convenient for us. And 2 by n pi is a factor, and sine n I will take it outside, and then I will say pi. So it means that I'm saying that all the arguments of the sign are the multiple of pi by 2. So here the big lesson that we are going to learn is, so here is, so an is um, is 2 over n pi, okay, and sine n, I will put a different number here. Okay, so this is pi. Sorry, I have to make it. Yeah, it is. Okay, here is. So it's a I can say that argument of sine is a multiple of pi by 2 because n represents the multiple. So it's a multiple of pi by 2. So when the argument of sine is a multiple of pi by 2, we need to look at the sine. And let's look at the sine here. So here is the sine that we are looking at. And it continues definitely and continues after. Now you can see that at this pi by 2, it is value 1. At this 3 pi by 2, it has, we are looking at all the odd values. So we are looking at 1 pi by 2, 3 pi by 2, then 5 pi by 2. So at 3 pi by 2, it is minus 1. And then 5 pi by 2, it becomes again plus 1. And 7 pi, so it means it alternates. With each pi by 2, it alternates between a positive 1 and a negative 1. So in order to cater this alteration, we go for n equal to 1, a1 is 2 by pi because this sign become 1. Whereas for n equal to 3, this become minus 1. So it become minus 2, the factor before it is minus 2. Similarly, n equal to 5, it become a positive 1, 2 by pi. For n equal to 7, it become a minus. So sign gives you minus, so this will be 2 by 7 pi. So if you just look at all of them, then you can conclude here very easily. Okay, I will try to conclude it now, and the conclusion is that an has 3 cases. This n, the n that I'm looking at right now, can be even. If n is even, then it is 0, because in this case the upper value and the lower value will cancel each other, as I've shown you. But if the n is odd, then I have 2 categories in the odd. The odds which are 1, 5, 9, and the odds which are 3, 7, 11. So for 1, 5, 9, I have positive sign and then 2 by n pi. For these other ones, these are also odd, but they are 3, 7, 11. We have a negative sign. Okay, so you can see here, this is a negative sign. So this is a plus and minus, so it's alternate between plus and minus. Okay, and now let's look at the bn. Bn are the weights for the sine function. Bn are the weights for sine terms. Okay, for the sine terms. Okay, and for the sine terms, these weights are 1 over pi, and then there's an integral from minus pi by 2 to plus pi by 2 sine nt dt. Now, if you look into sine nt behavior, okay, and here I given you when I put n equal to 1, this becomes sine t, and if I draw it, it looks like this. It has a period 2 pi. Keep in mind the period of sine t is 2 pi. So between my interest is only between minus pi by 2 plus pi by 2. So for that interest region, this is minus pi by 2, this is plus pi by 2. So these two are my region of interest. In this, I say there's a plus and there's a negative area. You see this? This is negative area and this is a positive area. So they cancel each other, and sine t, when I integrate between minus pi by 2 plus pi by 2, it will be 0. Now, if I look at sine 2t, the time period is here 2 pi by 2, so the period is pi. So when the period is pi, it means that it has shrunk half. Now it will complete its cycle between minus pi by 2 and plus pi by 2. And now again, it has some portion which is, this is half of the cap is above and half of the cap is below. So it definitely cancel each other. The areas plus and minus areas will cancel each other, and I will get 0. Similarly, sine 3t, the period is 2 pi by 3. And if I look at again between minus pi by 2 and plus pi by 2 time, in this time interval, there is a plus areas and there is negative areas, and they cancel each other. So whatever n I choose, so here is whatever n I choose, sine nt between these two limits, minus pi by 2 plus pi by 2. But keep in mind, these two limits are for the time, not for the angle. So for these two limits, it will always be sine nt will give you 0. Okay. So there is no bn, and when there is no bn, it means there is no sine part. So I can declare here no sine term. This sine term vanishes. Why vanishes? Because bn, no matter what n I pick, my bn will always be 0. Okay. So here is now, so in other words, my whole Fourier series for a square wave only consists of cosine terms. So Fourier series only consists of cosine terms. Of course, there is an A naught here. Okay, this is the A naught that I'm talking about. And this is just because I pick a wrong baseline. So if I correct my baseline, then there will be no A naught. But these cosines have an alternate signs. So there is a minus cosine, first cosine, then there is a negative cosine, then positive cosine, then negative cosine, positive cosine. So the negative sign alternates. Okay, and when the negative sign alternates, then we can have a mathematical expression where minus cosine x is equal to cos x minus pi. So if I introduce this one, then all my cosine will have positive term. The only thing that will happen is that I will introduce the phase term. So if I do this, now here is what it is, cos omega naught t. And in this case, I feel that you should not put this omega. The reason is because omega here is 1. So it's a cos t. This is cos 3t. If I remove this omega, because omega is 1, 5t. And now this is already in the compact Fourier series. I don't need to do any processing. Last example, we were doing that processing, that an square plus bn square whole under the root was cn. But here, we don't need to do that. We just took care of that trigonometric identity. This is the one that I'm talking about. This identity. So if I take care of this identity, then I don't need to really use the formula. So compact Fourier series is already in front of me. Because in compact Fourier series, everything is cosine, and there are phase terms. So I can see that there are phases, pi, minus pi. These phases comes because I have to convert the sign. This was a negative sign before, but to make it positive, I have to plug in this pi as a phase term. Okay. And now once we have the compact Fourier series, we can look at it. Now in case of this, I don't need the phase term because I'm not looking at Cn as a magnitude, rather I'm looking at Cn as an amplitude. So amplitude can take negative values. So I can say the difference between amplitude and magnitude. So in this book, he is not taking Cn as a, he is taking Cn as an amplitude. But if I want to go for magnitude, then I have to do a mod of Cn. So if I do mod of Cn, then of course the negative sign has to be taken care of by the phase spectrum. But since we are going with amplitude, in which we can say that Cn could be positive, Cn could be negative, then for negative Cn, because the only thing we are seeing here in Fourier series for our square wave is that some of the terms are negative, nothing else. So for negative, you allow them to go down. So you see, this one is negative. This one is negative. So if I allow them, then I don't need phase spectrum. So that's how it has. In this book by B.P. Latty, he is not considering it as a magnitude. Rather, he is considering it as an amplitude. So he takes care by putting the above and below these lines. So here we can see very clearly is that the DC term is the lowest term, lower than the next one. The terms that is really making a lot of impact here is this term. This is a very high amplitude term. And what is the frequency here? The omega here is 1. So omega equal to 1, and omega equal to 1, you remember, was a fundamental frequency. So the largest amplitude present in square wave is that omega 1. So in other words, if so I also can see that, for example, omega 1 is basically, you can think of it as a cosine that goes like this. And you can see that it is the one that is making most of the shape. Okay, look at this. So it's really dominating, and you can see very clearly that this is 2 by pi. The rest of the other one which are making those edges for you, like smoothing, these are the ones which are here, but they have a lower amplitude. They're high frequency. Another very interesting thing to see here from the analysis is that these even terms, so these even terms, this is even, this is even, this is even, this is even. So all those even terms are not there. Only the odd terms, and there is an alternate odd term. One is positive, other is negative, other is positive, other is negative. But there is no even term. So there is no even terms in Fourier series for square wave. Okay, so that's how the spectrum can tell you many things about the original signal. Okay, then there is a very interesting one. Okay, web page where you can see what we mean by Fourier series. Okay, I will copy it now here. Sorry, I will copy, and if I take it to my browser and paste it here, okay, and enter, then you can see very clearly here that this is a square wave, okay, and this square wave is made from all those waves. Look at this. This one is 0. This another one. So the one in the middle are the even one. 4f0 is 0. And now you can very easily see. So this is the fundamental frequency, 1f0. And as you move away from the fundamental, the other harmonics have very small amplitude. But overall, if you add all those, you will eventually end up with this particular square wave. You can see that very clearly. So if I increase the terms, you see, if I make it 13 terms, so if I make it, you see, if I make it 41 terms, I'm very close to square wave. Only the Gibbs phenomena is there on the edges. The overshoot, this is Gibbs phenomena, overshoots right here, right here. As many terms are added, still these overshoots will be there. Okay, I'm not able to suppress them. And if I increase further, 61 terms now, you see, I'm fairly closer to what I should be getting as a square wave. So the more and more terms I add, and look at this one, almost there. So there are now 124 terms I added, and almost a cleanup square wave. So how many I have used? I have used 124 harmonics. That's how I got it. Okay. Similarly, you can have what you call them a sawtooth waveform. So if you take a sawtooth waveform, look at this one, and if I reduce the terms, you see, now we have only 24 terms. And if I increase the terms, I will get a better and better approximation. You can see very clearly here. Check out. Check this out, okay? Same thing happens with the triangular waveform. Look at this triangular waveform. So if I increase the waveform, so here you see it's really a very nice smooth because very few terms I need after like 1 F naught, almost 3 F naught. I don't see any higher amplitude components. So 3 F naught is enough. So I can have only 3 components. And with these 3 components in the Fourier series, I can make a perfect, almost perfect triangular waveform. So it's really amazing to see how we are able to do it. So with that, we came down to the end of this lecture. So thank you very much. And we'll see you next time then. Take care of yourself.